8.1, the law of sines. So we're going to get into the law of sines, which is also going to lead us into the law of cosines. That'll be in the next section. But what we want to start with is congruency, because the whole idea of the law of sines and the law of cosines is for us to determine and be able to determine all the sides and all the angles of a triangle. Now, congruency means that two triangles are the same, meaning they share the same angles and the same lengths of sides. For us to guarantee that we have congruent triangles, we need to either have two sides and the included angle. If I have this side and that side, and I know what that angle is, there's only one side that'll finish that triangle, and there's only one possibility for what those angles are. So give me two sides and the included angle, and there is only one possible triangle that can make that happen. Or if I have two angles and the included side. So if I have a side, and then I have the fact that we have that angle, and the fact that we have that angle, if I continue out those sides, we see that there is only one possible place that they could intersect. Therefore, there is only one possible triangle that we could come up from this. The third way that we can guarantee congruency is to have the lengths of all three sides. Because if I have the length of one side, and I have the length of another side, and I have the length of the other another side, and I'm just going to do it like that, then there's only one way that these 2 points are going to match up. So that's going to swing through, that's going to swing through, and we would find that that has to be there, and this one has to be there, therefore giving us specific angles because we have the length of those three sides. There's only one way you can create a triangle from three set side lengths. So to guarantee congruency, or that we can build the exact same triangle as specified, either we need two sides and the angle in between them, two angles and the side in between them, or all three sides. If we have three angles and no length of side, then we have no guarantee that we're going to get congruent triangles, because if we don't have a length of any of the sides, then all we can guarantee is similar triangles. Because if I have the same angles and no length to compare them to, then we have what's called similar triangles. There's no guarantee. So essentially, to be able to come up with specific triangles from some information on the sides and angles, or to be able to determine all three angles and all three sides of a triangle, we need to have the length of one side and then any combination of two other pieces of information. Meaning, you give me the length of one side and then a length of another side and an angle, I can give you a triangle from that. You give me length of a side and the length and the measure of two angles, I can give you a triangle from that. So you need to have at minimum one length of a side and two other pieces of information. Either another side and an angle, two other sides, or two angles. So right now we're going to talk about the four different cases that we tend to look at. So we're going to call them, amazingly enough, case 1, case 2, case 3, and case 4. Now the first case that we're going to deal with is when we have two angles and a side. So we have two angles and a side. We don't care which order those are in, so that may be that we have angle, side, angle, or we have angle, angle, side, meaning that we have two angles and the side in between them, or that we have two angles and the side opposite one of those angles. Don't forget to close my parentheses there. So those are my two possible things that can happen in this case where I have two angles and a side. Case 2 is where we have two sides and one angle, but it's not the included angle. So two sides and an angle that's not included. Meaning it's the angle that's not in between these two sides. So it's not side, angle, side. So we refer to that as side, side, angle. For obvious reasons, we do not refer to it as angle, side, side. Nothing more need be said. So we have two sides and an angle, but it's not the included angle. So that's our second case. Our third case is that we have two sides and the included angle. So two sides and the angle in between them, so that would be side, angle, side. And then the fourth case is that we have three sides. We'll call the SSS for side, side, side. So these are the four different things that we can be given and use either law of sines or the law of cosines to find all the angles and all the sides of the triangle. Now when we do that, when we find all the angles and all the sides of the triangle, we call that solving the triangle. So we're given these pieces of information, any set of these, and then we solve the triangle to find all the other sides and angles. Now you may look and go, but wait a second, haven't we already dealt with this? We had right triangles and we used sine and cosine and tangent to find the other angles and sides, the ones that we were missing. Well, the key with this in the law of sines is we do not have to have right triangles. We can have what are called oblique triangles. An oblique triangle is any triangle that is not a right triangle. So oblique triangles. So now we don't need to have right triangles. So I want to add another piece of information with this. We've got that, but I want to point out now that cases 1 and 2 will be able to be solved using the law of sines. So that would be this section, 8.1. Cases 3 and 4 can be solved using the law of cosines. Section 8.2. So law of sines will get us through cases 1 and 2. Law of cosines will get into cases 3 and 4. And to be perfectly honest, when you get into law of cosines, That's usually the first step you do, and then you go to the law of sines to finish it up. Along the way, though, realize that there is another piece of information that we'll be able to use to help us with this, and that's the sum of interior angles. We know that the sum of interior angles for any triangle is 180 degrees. So if you think of that in this first case, and we'll take advantage of it here, and you'll also end up taking advantage of it later on, but here it becomes obvious that if I have two angles in my triangle, then it's very easy to find the third angle using the sum of interior angles. Okay, so we're going to focus in 8.1 on cases 1 and 2. Angle side angle, or angle angle side, where we have two angles and one side, and side side angle, where we have two sides and the non-included angle, the one that's opposite a side, not in between them. So let's find out what the law of sines is. To do that, we're going to look at a basic representation of a triangle. I should say a generic representation of a triangle. So I've got this triangle here. I'm going to call this A, B, and C. Remember that what you call A, what you call B, and what you call C does not matter. So C does not necessarily have to be the longest side of a triangle. Just keep that in mind. But we will follow the notation of the side opposite an angle is going to have the same letter, just lowercase. So the angles will have uppercase, A, B, C. The sides will have lowercase, A, B, C. And for the sake of convenience here, I'm going to put this B over here. And you'll see why in just a moment. So now we've got our triangle ABC. What I'm going to do is I'm going to put a height h here, because we know if you have a triangle, you can find the area of the triangle if you have the length of the base and the height of the triangle, right? And I'm also going to take this point right here and call it D. And that'll become apparent in just a moment why I would do that. So now we can see that I have my main triangle ABC, but I also have created two smaller triangles, ABD and CBD, both of which share h, the height. And those are right triangles, which is what we're going to use to our advantage. So if these are right triangles, then I can look at angle C and angle A. So let's start with angle A. And I say angle A, well, if I want to find the sine of angle A, that is equal to opposite over hypotenuse. So that's H over C. If I solve this for H, I just multiply both sides by C, and I get H is equal to C times the sine of angle A. I'm going to do the same thing over here. The sine of angle C is equal to opposite over hypotenuse. So that's H over lowercase a. And I mean, if I solve for H, I multiply both sides by A, I get H is equal to A sine of C. So that's great, but now I have H equal to C sine of A. I have H equal to A sine of C. Obviously it's the same H, right? So I can say that C sine of A is equal to A sine of C. And if that's the case, I can divide through, well, should say, I can divide both sides by sine of A to get that out of this side. And I can divide both sides by sine of C. So basically I can divide by sine of A, sine of C. If I do that, then I end up with C over sine of C is equal to A over sine of A. So now I have a relationship saying that the ratio of the length of side C over the sine of the angle C is equal to the ratio of the length of side A over the sine of the angle A. And if I were to go through and do this again, but make H go from one of the other peaks, like from C, have it go to there, or from A, have it go from there, I could do the exact same thing and show that that also is equal to B over sine of B. And that is the law of sines. So let me put this up here. Law of sines, A over sine of A is equal to B over sine of B is equal to C over sine of C. And yes, technically you could flip those two. People usually don't, because it's easier to just always keep it in the same pattern. But since those ratios are equal to each other, there's nothing that stops us from saying the sine of A over A is equal to the sine of B over B is equal to the sine of C over C. So those are both true from this little derivation that we just did here, and that is known as the law of sines. And we should be able to see from this that if we take any two of these ratios and work with them, as long as we have the length of a side, the measure of the angle opposite it, and then either the length or measurement, the length of a side of another side or the length of another angle in the triangle, that we can then finish up the proportion relating those. And once we do that, we have guaranteed that we have two angles, which means we can find the third angle by using the sum of interior angles. And then since we have that, and we have an angle and the side opposite it, we can use that to find the other side. Now I know that sounded like a lot, so let's build a triangle with some information and go through using the law of sines. Okay, for convenience sake, I'm going to look at an example that I have on hand. So we're going to solve triangle ABC if angle A is equal to 28.8 degrees, angle C is equal to 102.6 degrees, and side C is equal to 25.3 inches. Okay, so I'm just going to get that out of the way. So now that I have that, let's first draw the triangle. It's always easier to do these things if we can visualize it. So draw the triangle. I'm just going to draw it here. It doesn't have to be huge. Okay, so we've got A, B, C, and I do not guarantee that this triangle is drawn to scale. To be perfectly honest, I don't care if it's drawn to scale. I just need to be able to see what relationships I have. So, and that's A, B, C. Angle A is 28.8 degrees. Angle C is 102.6 degrees. And side C is 25.3 inches. So 25.3 inches. So now we have, and I'm just going to make that look more like a 25. There we go. So this is what I have. Now what do I need to find? I need to find angle B, side A, and side B. That's what I need to find. How am I going to do that? Well, the first thing I see is I have two angles, so I just need to find the third angle. How do I do that? I just add these up and subtract it from 180. Let me grab my calculator. It's over to this side today. There we go. It's got a calculator. So I have 28.8, 102.6. So I add those up and I get 131.4. And I'm going to subtract that from 180. And I get 48.6 degrees. And what I'm going to do here is I'm going to change to a different color just so we know this is what was given and this is what we're finding. So I'm going to put what we're finding in red. So we just found out that angle B is 48.6 degrees. And how did we find that? We added the two angles together that we have and subtracted from 180. So that was easy enough to find, sum of interior angles. Now we need to find the length of these two sides. And that can be found by using the law of sines. Now I am going to give you a piece of information. It's not critical here, but it could be critical in other situations. It's always best to use the information that you were given rather than information that you calculated. So if you have a choice between using values that were given as part of the problem to do the next calculation, or using numbers that you calculated yourself from numbers that you were given, it's best to take the numbers that were given. So here what that means is, I obviously have C, the length of C, and I have the angle C, and I was given the angle A, so I'm going to use these three values in the law of sines to find side A. I'm going to find that one first, because I was given all three of these, so that means I'm working off of numbers that I was given directly as opposed to ones that I calculated. As I said, in this particular situation, that's not going to be critical. And the reason it's not going to be critical is when you're dealing with two angles that were added together and then finding the other one, it's not like you're going to run into errors from that. You're not going to find out that you had to round your other angle to some random place, because you're going to add them together and it's just going to be the precision of those two measurements. But if you were dealing with having found a side through a calculation, then you may have had to round that, and that could affect your other numbers. So we want to find A. So what we're going to do, we've got C, C, and A, right? We've got angle C, side C, and angle A. So we're going to take A sine A and C over sine C and set those equal to each other. So I'm just going to put that here. So I'm going to get A over sine A is equal to C over sine C. And I'm just going to fill these in. So I'm looking for A, so I'm going to leave it as A. Angle A is 28.8. So sine of 28.8 degrees. C is 25.3 over sine of C, and angle C is 102.6. Okay? Critical thing. Make sure your calculator is in degrees. So I'm going to set my calculator into degrees. Okay. And if you want to verify that, take the sine of 90 degrees. Sine of 90 degrees is 1. Okay, I'm in the right measure. If you took the sine of 90 radians, you would get something completely different. In fact, if you took the sine of 90 radians, you would get 0.8939, so that would tell you, oops, I'm in the wrong one. But just make sure your calculator is in degrees. So mine is, so I'm good. So now I just need to solve for A, and the method I always use when I have a proportion here is I just multiply the diagonal and divide by what's opposite. And if you were to solve this out, you realize, well, if I want to get A by itself, I need to multiply both sides by the sine of 28.8 degrees, which means that's going to get multiplied over here, and you're going to end up multiplying this times this and dividing by that, which is multiplying the diagonal and dividing by what's opposite. That will always work for solving a proportion. Remember, proportion is just a ratio set equal to another ratio. So anytime you're solving for one of the 4 items in a proportion, multiply diagonal and divide by what's opposite. So I'm going to take sine of 28.8, which is approximately 0.48175336, etc., etc. I'm going to multiply that by 25.3, which now gives me 12.188367, etc., etc. And then I'm going to divide by the sine of 102.6. The sine of 102.6 is approximately 0.9759, etc. So I divide, and I get A is equal to 12.48914, that did not look like a 4, 470565, that's as far as my calculator gives me. Now, remember we talked about precision and accuracy? And I said, okay, now that we've talked about it, we don't have to worry about it. This side is to 25.3 inches, so basically to the nearest tenth. So I'm just going to round this to the nearest tenth. A is equal to 12.5 inches. So 12.5 inches. And that's all I'm going to do for that. So that gives me A. So the question is, how do I find side B? So I'm going to put that here, 12.5 inches. So I've solved that. Now side B, remember this is not a right triangle, so you cannot use Pythagorean theorem to solve for the third side. So what are we going to need to do? We're going to do law of sines again. And again, use as much of the given information as you can. So I could technically use A over the sine of A equal to B over the sine of B. But if you look at that, I'm using a number that I rounded and a number that I calculated in only one of the original values if I do that. What I want to do is use as much original as I can. So C and C, the lengths of side C and the measure of angle C, those were given. I want to find B, so I'm going to have to use my calculated B, but at least that means I'm only using one calculated number in there as opposed to 2 or 3 of them. But I'm going to do the same thing. I'm going to say B is, not B is equal to, I'm trying to find B. B over the sine of angle B, which is 48.6, is equal to C, 25.3, over the sine of angle C, 102.6. So B is equal to, multiply that diagonal and divide by what's opposite. So the sine of 48.6 is approximately 0.750111, etc. I'm going to multiply that by 25.3. Gives me approximately 18.9778, etc. And I'm going to divide that by the sine of 102.6. And remember, well, you don't have to remember that, but that is still 0.9758024, etc. Because we already did that over here. So when we divide, we get 19.448414857. Again, the original measurement of the side was to the nearest tenth, so we're going to round that to the nearest tenth, and B is equal to 19.4 inches, so 19.4 inches. And we have now solved this triangle. I should put this angle in here, 48.6 degrees. We now know all three angles, 28.8 degrees, 48.6 degrees, 102.6 degrees. We know all lengths of sides, 12.5 inches, 19.4 inches, 25.3 inches. So what did we do? We're dealing with case one here. If I didn't state that earlier, case one where we have two angles and a side. So what we did was, since we had two angles, we just used the sum of interior angles to get the third angle. And then we used the law of sines to get each of the other two sides. And we used as much of the original information as possible. So to get the length of side A, we used length of side C and the angle C and the angle A. So we had all numbers that we were given and calculated. If you got confused over here, all I was doing was multiplying the diagonal and dividing by what's opposite, or solving for A. If I solve this for A, then I'm going to multiply both sides by the sine of 28.8 degrees. When I do that, it's going to disappear from over here, and I'm going to end up with this value, sine of 28.8 degrees, multiplied by 25.3, divided by the sine of 102.6 degrees. And as I said, that will always work out to be the product of the diagonal divided by what's opposite the one you're working for. So there we go. So that is an example of case one where you have two angles and one side. Anytime you're given two angles, take advantage of that and find the other angle. Once you have an angle and a side opposite it, then if you know any other angle or any other side, then you can find another angle or side. And then once you do that, you can find the third angle or side using the same thing. So that's what we did here, and that's case one for the law of sines. Tune in next time for case two.